Hi everyone, in this video I am going to introduce a parameter called figure of merit. Figure of merit is indicated by omega naught and one more transistor which is a pass transistor. Okay, very interesting topics. So first one is figure of merit. What do you mean by figure of merit? Figure of merit is nothing but the ratio of transconductance to the gate capacitance. Okay, so we can write the definition. It is defined as the ratio of transconductance to the gate capacitance. Gate capacitance is indicated by Cg and transconductance is nothing but indicated by Gm. So it is indicated by figure of merit is indicated by omega naught. So omega naught is equal to Gm by Cg. Omega naught is equal to Gm by Cg. So transconductance Gm. What do you mean by transconductance Gm in terms of Cg? Where transconductance Gm is equal to, it is nothing but transconductance Gm. Transconductance Gm. It is in terms of, now we are writing the expression for the Gm in terms of Cg. Cg mu Cg into mu Vgs minus Vt by L square. This is what the Gm. So Gm is equal to Cg mu by L square into Vgs minus Vt, because the transistor is said to be in saturation region. That's why we have considered this one. Otherwise, we will consider only one equation. Okay. So what we need, Gm by Cg. So therefore, omega naught is equal to Gm by Cg, that is equal to Cg gets cancelled, mu by Vgs minus Vt divided by L square. Cg gets cancelled. We will be having only figure of merit omega naught is equal to mu into Vgs minus Vt. So in saturation we know, in saturation Vgs is equal to, in saturation what is that, Vgs, not Vgs, sorry, Vds is equal to Vgs minus Vt. Okay, in saturation we can write Vds is equal to Vgs minus Vt. That means at that point only saturation comes or saturation starts. So Vds is equal to Vgs minus Vt. Okay, substitute that in the above equation, then simply, therefore the figure of merit omega naught is equal to mu into Vgs minus Vt. We can write mu into Vds by L square. What do you mean by this one? This is nothing but tau, 1 by tau. So since tau is equal to L square by mu into Vds, L square by mu into Vds. Okay, so we can say this is nothing but omega naught. Omega naught is inversely proportional to, we can write the omega naught is inversely proportional to tau, electron transit time. Okay, so note the figure of merit, is defined as reciprocal of, electron transit time, tau. Electron transit time tau. It is a reciprocal of electron transit time tau, because we have seen that tau is tau, how we have got the expression. Okay, so this is what the figure of merit. Another type of concept we are going to learn today is pass transistors. Pass transistor. What do you mean by pass transistor? Why it is said to be a pass transistor? Suppose if you are taking a transistor like this, that is other than the conventional way how we are representing. Let us give a logic 1 here. Okay, let us give a logic 1 here. What about the transistor? The transistor is said to be in on or off state. It is in on state because it is having sufficient input voltage between gate and source. Okay, we can call it as source or drain. We can call it as drain or source. Okay, depending upon the usage, we can interchange these two. Okay, so the transistor is said to be non-state when there is a logic 1. Okay, logic 1, or we can also say here the input voltage should be greater than Vt. The input voltage what we are giving between gate and source is nothing but we are giving that input potential VGS as just above the Vt, so that the transistor is said to be in on state. Okay, now let us consider three transistors are in cascade. Let us consider three pass transistors, in cascade. See here we have taken only one transistor. This transistor is said to be a pass transistor. That means when input is given here, when transistor is said to be on state, there exists a short circuit path from here to here. That is also Vin. Okay, output equal to input. We can say output equal to input when transistor is on. So V out is equal to 0 or any residual value when transistor is said to be off. Okay, so this is what the pass transistor. Depending upon the input voltage here, the transistor is said to be either on or off. So let us consider three pass transistors in cascade. And one more point is here, assume that when input is equal to logic 1, what is the output voltage? Output equal to input. But when input is equal to logic 0, we can say the output voltage is not equal to input voltage. Output voltage V out here, that is not equal to input voltage, because the entire input voltage will be stopped here only. There is no channel as well. That's why there is no output voltage. So consider three pass transistors in cascade. This is the input where we are applying, and this is the output. Now let us consider the channel threshold voltage. For this one is Vt, and this is also having something like Vt, and this is also having something like Vt, and so on. It is having number of Vts in cascade. Okay, when input to something like VDD is applied at this particular point, what is the output at this point? Okay, we are assuming that all these are in on state. We are assuming that all these are in on state, or we can say it is in okay, VDD. Now when VDD is connected at this particular all these points to the gates, then gates are on state. That means we have given initially the transistors are in on state. So now VDD is given here. So what is the output at this particular point? Can you say VDD exactly? No, because there is a drop across this pass transistor which is said to be a threshold voltage. So VDD minus VT. Next here it is also VDD minus VT. Another thing is going to be added with this. Okay, but when you are going for the third equation, then we can say VDD minus VT again plus previous ones. So VT here, suppose if you are taking 3 pass transistors, they are having common threshold voltage, then we can say VDD minus 3 into VT. Suppose 10 pass transistors are there, so then VDD is equal to output is equal to VDD minus VT for n number of times or 10 number of times. So how many we have, that many will be added. So there is a degradation in the level of the output voltage. We will not get 100% output voltage because of the pass transistor logic. Okay, because of the drop across the junction, drop across the channel where the source and drain electrons are going to be flowed. Okay, so in general, we can write, or we can say the output from two or more pass transistors is V out is equal to V input or VDD minus V out is equal to V input minus VTP. What do you mean by VTP? Where VTP is nothing but threshold voltage of all pass transistors. Okay, this is the story related to the pass transistor. Okay, thank you.